Welcome everyone today to this London Climate Action Week event. So we're going to be talking about advancing health with next-gen climate intelligence, looking at both climate projections, some AI and also Earth observation. We've been very kindly hosted by Wellcome, and Felipe is just going to come up and give some opening words and a bit of housekeeping for us. Thank you very much, Felipe.
Thank you. Well, first of all, welcome to everyone in the room and online. Thank you for joining us today. I'll keep this brief. At Wellcome, our climate and health work is centered on a practical mission, which is to put health at the heart of climate action. And a key challenge to deliver this mission is translating advances in climate science into decisions that improve global health. There's still a gap between what climate data is available and what is actually possible in the health context. And that gap shows us in different ways, whether it is the relevance of variables, the scale of analysis, or simply the ability to move from data into real-world actions. Closing the gap is not a luxury, it is a necessity. It is what will determine what climate intelligence deliver meaningfully to have impact on health. And that is the context of today's session. The session is designed to move the conversation forward by focusing on use rather than on production, and by creating a space for direct input from those working at the interface of climate and health. So what we need from you is clear, candid feedback on what works, what doesn't work, and where the effort needs to shift. Particularly, for us, it's very relevant to know where the effort from the funding decision makers has to shift. And that input, we would really like to ask you to be unapologetically practical, because that's how priorities are set. So I encourage you to engage on that basis. I'd like to close by thanking our partners at the European Space Agency, CMIP, WCRP, and all the speakers and panelists for contributing today. I'm looking forward to this discussion.
Okay, thank you very much, Felipe. So first up, we have Helene here, is one of the CMIP panel co-chairs, and she's going to give you a bit of an update on what we can be expecting from CMIP 7.
Okay, thanks, Eleanor. Thanks everybody for coming here for this event. As Eleanor said, I'm the CMIP co-chair. I'm also a science fellow at the Met Office, and you'll see me a bit later talk about some Met Office work as well. So, this is partly a CMIP event. So what is CMIP? For people who don't know, it's the Coupled Model Intercomparison project. It's a flagship project of the World Climate Research Programme. And we provide climate projections and other experiments to understand the past, present and future climate change. So CMIP and the infrastructure have really become essential to the Intergovernmental Panel on Climate Change, or IPCC, and other international and national climate assessments. But increasingly, we're seeing the data from CMIP being used for many other purposes, and hopefully that's why many of you are here today. So the last phase of CMIP was CMIP 6. We had many models and institutions and experiments involved, and there is a huge data resource there. We have nearly 25 petabytes of data for you to see, hosted on a number of Earth System Grid Federation nodes around the world. And this figure at the bottom shows the patterns of warming from the CMIP experiments at different levels of global warming. And this was in the IPCC report. Almost all the figures on future climate in the IPCC report derived from CMIP. I was one of their coordinating lead authors for the AR6, so I can attest to that. But as we said, it's not just used for IPCC, increasingly by a wider audience. So we're now in the next phase of CMIP, CMIP 7. So I'll give you a bit of an update and tell you what's new and what's coming up. So CMIP 7 will look a bit different to how we've had it before. We've tried to create a smaller subset of experiments that can be done in a shorter space of time by the modelling centres around the world. And we call that the assessment fast track. So this will include experiments of the historical period, so we can tell what's happened in the recent past and why, as well as the scenario experiments, so the going into the future to 2100 and beyond. And this will be used both for things like IPCC, but for other users, and including things like the downscaling for CORDEX and for the impact studies like ESA. So new things in CMIP 7. So the scenarios will not be concentration driven, they'll be driven by emissions. This is key for policymakers because policies are defined in terms of emissions and not concentrations. It also means that we can understand the uncertainties in the carbon cycle, which are neglected if you if you run on concentrations. So this is going to enable much more realistic projections into the future. Also new for CMIP 7 is we have invested a lot of effort into updating historical forcing data sets from 2014 to close to the present day. This is a huge effort, but it's absolutely essential if you want to say why the last few years were so warm, for example. We can't do that unless we know about the emissions, the volcanic forcing, the solar forcing, and so on. And new for CMIP 7 is a new population data set, which Lawrence will speak about. Also new for CMIP 7, and anybody who's on the social media may well have seen this, is the new scenarios. So that we now have a new set coming up to 2100 and beyond. There will be 7 scenarios, including 3 which have an overshoot type behaviour. The key messages to take away from these scenarios is that the highest scenario, it does have lower emissions than the 8.5 scenario, which many people are familiar with. And there are 2 reasons for this. Primarily, we have followed a middle of the road pathway for emissions for the last 10 to 20 years. And so we have pushed back the possibility of such high emissions for some, for a few decades. And also the cost of renewables has made it much less likely that we'll go quite so high. However, even in spite of that, the warming estimate for 2100 is still expected to be around 3.5 degrees from the models. And if we have models with high climate sensitivity, it could certainly go above that. At the low end, even the lowest scenario overshoots 1.5 degrees. And this really will need large-scale carbon dioxide removal. And, many of the, as I said, 3 of the scenarios include these overshoots. This is really important for understanding how society can respond to these overshoots. Will we pass tipping points? What will be the impact on health temporarily or longer term, for example? So one of the things that we've done in CMIP 7 is we've put a lot of effort into creating a data request. We've looked at different sectors to ensure that we're meeting people's needs for data. And one of those was an opportunity around health impacts. So that's looking at air pollution, the climate system. There's daily and hourly outputs which allow for this sort of resolution. There's the heat indices variable group, which has daily and maximum daily wet bulb globe temperatures, as well as the NOAA heat index. And these will all be calculated within the model, so it will allow you to have consistent downstream impacts. So if you're interested, please review this. There's a paper online. If you can't write it down now, please feel free to come and talk to us in the lunch break. You might want to know where you can access the data. We have the data will be on the Earth System Grid Federation, on Metagrid. It's often also available on other sources such as Copernicus Climate Change Service and Pangeo or Earth Mover. But what I would say is if you go to a third party, please always go to ESGF and check the errata, because with the best will in the world, mistakes come up. The third parties do not correct the data if there's an errata, whereas it will always appear on ESGF. So you can access that with the see from the QR code. Another new thing for CMIP 7 is you can get the full data, but we are also making available this rapid evaluation framework. So we will have a portal where we've defined some key metrics across the space of users, where you can see these metrics as they come, as the model data is uploaded to ESGF. These metrics will be produced and available on this dashboard. So please do take a look as they come up. There's not enough data there for them to show at the moment, but they will be there shortly. But this is a great innovation that we've really invested in. Finally, one thing that's really defined CMIP for the last 20 to 30 years is that we've been constrained or driven, if you like, by the IPCC timelines. And we're really looking to move to a more quasi-operational capability, if you like. So looking to have more recent updates on the historical period and more regular future projections. We've suggested perhaps every 5 years aligning better with the global stock take, but that might become even more frequent. So this is something we're really looking at now, and we really want to build this as a sustained mode with sustained infrastructure, and supported still by research which will further improve these historical and future projections. So thank you so much for your time, and now I'll pass to Lauren.
Thank you very much. Thank you, that was a really nice overview. So now I'll be talking about population density data. So my name's Lawrence Hawker from the University of Bristol, and I'm co-lead of the FuturePop project, along with Andy Tatum at the University of Southampton. Okay, so what is FuturePop? So in this project, we are producing gridded maps of population count until 2100 for the 5 SSPs. Now, what's really nice about this project, and we've been very lucky with, it's sustained for 7 years project. So it started last year. So yeah, the sustained effort, and we feel we can really make a transformative change in this area. So how do we produce future population data? So we need gridded data from the present day. So we use the Wellcome data. So that's the partners at the University of Southampton. And this data comes from a wealth of census data. And then we have settled data on settlements. So this is really advanced in the last few years with remote sensing capabilities. And then we have data on covariates. So this is basically how likely someone is to live in a particular pixel. So people tend to live near roads, for instance. So this creates the Wellcome data. And then from that, we use population projections from the SSP database. So we're using the latest version, which is 3.2. And then we have a model for probability, settlement probability layer. So this is essentially how areas might grow or indeed shrink of settled areas. So what does this data look like? So let me, in the bottom left-hand corner there is Kinshasa. So this is quite a rapidly growing city. And the bottom right-hand side here is Rome. So this is a shrinking city or urban area. Now this data is available. So there's a QR code just here. And as Helen mentioned, it's part of the CMIP 7 forcing data. So how does it fit in? So yeah, population density is brand new for the forcing data. So there's kind of a lot of understanding of what is required. So what we needed to produce is a harmonized and consistent population data set from 1850 to 2100 and beyond, actually, to 2300. So this work was led by Dominic Popotny from Szczecin in Poland, and he combined best data sets from each of these timeframes, basically, to create this population density data set. And this is available on ESGF. Ideally, we would just have a version that is consistent across all time points, but at this stage in time, we need to stitch together these different data sets. Why this is important? So for the forcings, for instance, CMIP really need population density. And looking a bit further down the line, impact modeling from CMIP, and indeed any impact modeling kind of really needs information on population. So what's coming up in FuturePop? So next month we are planning to release FuturePop version 1. So this is updated methods, and the really key point is our grid cells are now going to be age and sex disaggregated. Now there's a few plots here of of how demographic shifts. This is in Zambia and Brazil, so apologies for people in your rooms, a little bit small. Let me highlight you to the bottom right-hand plot here. So this is age-sex pyramids for these two countries. Zambia on the top row, Brazil on the bottom. 2025 on the left-hand side, 2100 on the right-hand side. So as we can really see, like Zambia, for instance, is a very young population at the minute, but by the end of the century, the population is getting much older, and same for Brazil. So I think this is really important to try to understand the health, climate and health impacts. And we're doing a whole bunch of other things. We're having urban projections, uncertainty layers. We're just going to keep updating this. So there's, watch this space, basically. Right, and my last slide, kind of a tip to the climate and health. So we've been producing some training materials. So the website is almost live now. So this is training materials in R and Python, basically how to use climate data and our FuturePop age-sex data to try to understand some climate and health exposures. So at the minute we have heat exposure, super relevant now, of course, and dengue, but we're kind of looking to expand this. We're discussing with CMIP, Massive Countdown, and a few others, but we really want people to interact with us, like to help understand how this data can be used, to test it, to see where it looks good, to see where it looks not so good. So please do reach out about that. Last but not least, I just want to highlight PopMIP. So this is another MIP that I've decided to set up. So basically the idea of this is to kind of look into population data. So there's a QR code with expression of interest there. And that's kind of me for this. Thank you very much.
Great. So I'm Eleanor Wellcome from the CMIP International Project Office, but I'm just going to provide a bit of an update on the coordinated regional downscaling experiment on behalf of our CORDEX colleagues. So give you a bit of an idea of what you can expect from their upcoming data and also some of their high resolution activities. So just for those who maybe are not familiar with CORDEX, their kind of vision is to advance and coordinate the science and application of regional climate downscaling. So they're driven by the global climate models, but can then simulate at much higher resolutions that are much more relevant to regional information. They do that in a very capacity building sort of global partnership and collaboration effort. So they have 14 domains around the world, and that covers all global regions. So you have, for example, CORDEX Africa, North America, Australia as well. So they have, similar to CMIP, a common experimental protocol, and the output is available on the ESGF as well. Also, like CMIP, it's not sort of funded directly, but is a sort of amalgamation of research funding and in-kind contributions, or especially those working for sort of national climate scenarios. So currently, what is about to be published very soon is CORDEX CMIP 6. So that is the downscaling of the CMIP 6 models. There's 900 simulations are planned. That sort of graph on the left there, you can see the sort of numbers that are published, completed, etc. for each of the domains. Probably want to have a look at that in the slides after, it's quite small. There's only currently 4 domains of significant activity. That is largely due to funding restrictions in many regions. So that is an area of kind of trying to build capacity that needs to be addressed. But as I said, it should be available very soon on the ESGF. That QR code lets you know where the simulation status is, so you can have a look. New for the assessment report 7 from CORDEX is they do a CORDEX core, which is maybe somewhat similar to the CMIP assessment fast track. It's their contribution to the IPCC report cycle, and is that sort of homogeneous data set of high resolution regional climate information for the major inhabited areas. So we go down to 9 domains there. So they use 3 GCMs, global models, and 1 scenario, and then 4 specific regional climate models. What they're also planning to do is use the machine learning emulators to allow for a kind of quick downscaling of the new CMIP 7 data. And that will mean that there will be greater alignment across the working group reports than we've seen previously. So now a quick spotlight on one of their flagship pilot studies. So these are research activities that really focus on subcontinental scale and sort of areas of specific interest or processes. And it means they can address sort of specific challenges. So one sort of example here, which is relevant for where we are, is urban environments and regional climate change, RCC. So they're looking to the sort of effect of urban areas on the regional climate, as well as regional climate change impact on cities, using sort of coordinated activities. So currently in the regional climate models, often the urban parameterization scheme is turned off. Cities are typically represented as rocks and land cover data, and you only have sophisticated representation in short-term runs. But in this flagship pilot study, they did, for example, a 6-month run for heatwave events in 2020 in Paris. And that kind of then had ongoing simulations over the sort of decadal simulations for historical and scenario for cities worldwide. And that was using RCMs that had urban canopy models, so much more sophisticated. And there was over 30 institutes involved. And this figure just shows how much more detail you get when you're moving from the 50-kilometre down to the 3-kilometre. So their kind of objective, one aspect was looking at this urban heat stress island, and that's a particular sort of indicator for human discomfort. I think we're all feeling that today outside. So they've been looking at that specific sort of indicator and looking at the diurnal cycle, minimum, maximum values, and seeing how much added value is offered by these more complex parameterizations and the higher resolution. So there's different sensitivities to different input variables and the sort of interactions between the meteorological variables and those sort of intervariable relationships. So they're also looking at how it varies between heat wave and non-heat wave days. So if you just look at some of these kind of outputs, we see that when you include those urban canopy models, you simulate much higher nighttime heat stress, and which more replicates what's actually felt in these urban areas. And you see a sort of more pronounced urban effect from the simplified wet bulb globe temperature than the wet bulb temperature, because there's a larger dependency on the air temperature. It also shows that there's a better representation of the diurnal cycle, and that gives sort of more information for health and sort of heat alerts in these heat wave events. So it shows how much benefit is seen when using these more complex and higher resolution models. So that's just an update from them. If there's any questions, we may not be able to answer them directly, but we can definitely put you in touch with those who can. So now we're going to move on to a short section looking at how further examples of how CMIP and CORDEX data is used for heat heat relevant impacts. So we're going back to Helene, who has got an example from the UK Met Office and partners.
Okay. Right, thank you. As I said, I'm now switching hats now. Now I'm very much in my Met Office hat and presenting this on behalf of some of my colleagues. So obviously it's really topical at the moment to be talking about overheating, the built environment and people most vulnerable to heat. But hopefully we'll also show how the CMIP information through UK CP 18 and multidisciplinary partnerships can provide the evidence to inform UK adaptation. So what's the division of labour? So CMIP is really providing the internationally coordinated global experiments and emissions pathway. And this is defining much of the large-scale climate signal and the uncertainty range, while we have UK CP18 translating that into products that are more directly usable in the UK. And that includes probabilistic estimates and higher resolution regional and local projections. So this is really important for the health research. So CMIP has given this uncertainty envelope, but we need UK CP18 to give that spatial and temporal detail to give the impact modelling. So I'm first going to talk about one really important partnership, and then I'll go into more detail of a specific example looking at overheating in schools. So the Health Protection Research Unit in Climate Change and Health Security is a really important partnership that sits at the interface between climate science and public health policy. So this partnership's really interested in the hazards like extreme weather. Extreme weather and health. That's completely thrown me now. So UK CP18 is clearly really important for this to identify who is most at risk, and for the UK Health Security Agency, this information is important to turn it into preparedness, guidance and policy. So now if we focus into a real example, so here we're looking at overheating in schools. Now this came about because of the third UK climate change risk assessment, which identified that there was a real need to improve the spatial detail in the national climate risk assessments. And so as a result of that, there was a UK climate resilience programme with the Met Office working with UCL and the Department for Education to develop the spatial climate risk assessment framework, which was then applied to the English schools estate. So this can then really support on the ground action. It's not the model or framework isn't limited just to schools, but has also been applied now by the Ministry of Justice to prisons, and we have similar workflows for other housing, care homes, etc. So this is the basic model or framework. We talk about the hazards, the exposure and the vulnerability. So the hazards are the climate-related event itself. So in this case, high temperatures and heat waves. Exposure is where the assets or the people are. And so there we've got the locations of schools across England, and vulnerability is how susceptible these assets are to harm. And so we get this information from the Met Office, the Department for Education and UCL, and this comes together with the CLIMIDA risk assessment to actually produce estimates across the full school estate. And so if you look at the results, every dot here represents 1.1 school. And so you can see in a 2-degree world and a 4-degree world, we have many more school days where we exceed 35 degrees. Even in a 2-degree world, there are some schools that will experience more than 15 days of higher than 35 degrees. And this was published by the Department for Education. And of course, this is a real issue for learning and so on. And so this has a real impact. As we said, this information was published by the Department for Education in the 3rd National Adaptation Programme. We're looking at it for other applications, such as the Ministry of Justice. We have a climate ambassador scheme. And so just to finish off, this is really not climate science on the shelf. This is climate science in action, going from CMIP through to UK CP18 and the risk framework to government policy. And so CMIP isn't just background science. CMIP is really fundamental to these adaptation plans.
Gillian. Next up, we have Eunice Lowe from the University of Bristol and BREED, and she's going to tell us a bit about the BREED project. Thank you very much.
Hi everyone, it's nice to be here. So yeah, I'm representing the BREED project funded by the Wellcome Trust. It is about attributing health impacts to extreme weather and long-term trends in climate to the human causes, so human-induced climate change. Particularly, we have a focus on health equity as well, so looking into equity and inequity, hoping to use our science also to inform policy. So in this particular paper that I'm going to talk about, is a focus on Brazil, which will come up in the next slide. But primarily, we've used the detection and attribution MIP data in CMIP 6 to understand, the different components or contributions of different radiative forcing on health impacts in a Brazil case study. So in general, in DA-MIP, there are multiple historical runs, ones that focused on only the natural forcing in the atmosphere, and also greenhouse gases, aerosols, and stratospheric ozone. We've particularly focused on the natural forcing and the greenhouse gas forcing, which is the human-induced one. So, so the team has used the detection and attribution MIP data from 13 CMIP 6 models. Altogether, I think there are 113 ensemble members within them, particularly focusing on the factual scenario, which is what happened in the past, historical scenario, and then understanding the contribution of just the natural forcing and the anthropogenic forcing to that, and then translating that into the health outcomes as well. So it is a rather small graph here, but as you can see on the top left corner, we're looking at time series of temperature averaged over Brazil from 1960 up to the recent years. The green line is the natural forcing run. So in a counterfactual world without human emissions of greenhouse gases. The black line is the observations. The yellow line is the all forcing run, so natural and also anthropogenic. And you can see how the factual simulations or historical observations of climate match the all forcing run. So it can't be explained really only by natural forcing or variability, which is the green line. We've done traditional detection and attribution for trends on it. So it's optimal fingerprinting using total least squares regression to find that actually overall in Brazil in the period of, I think, 2000 to 2018, so an 18-year period, there's been about 0.9 degrees Celsius attributable heating to anthropogenic climate change over the region. There are geographical differences within the country. So that's a map of the temperature difference in just near surface air temperature between the all forcing scenario versus the only natural counterfactual scenario. So of course, it's hotter with the greenhouse forcing as well. So we focus on the health impact. So the team has collaborated with a cohort in Brazil, which is called 100 million cohort. So they have over 100 million participants in their cohort, and they've been following their health, and they've got a wealth of health data of these people in the country. It is about over half of the whole population of Brazil. This cohort is mainly focusing on people who are more on the low income side. So we also can understand the inequality part of the country as well. Overall, Brazil has a population of 213 million, I think. All right, so we've applied, we've used the 100 million cohort health data. We've used epidemiological models that show us what's the relationship between exposure to temperature and mortality outcomes. We've combined those with our DAMIP simulations between historical natural and historical ore forcing. And then we've come up with these statements here. So basically, over the 18-year period that we've looked at, there have been over 75,000 heat-related deaths that can be attributed to human-induced climate change. That's a big number. It's over an 18-year period. So on average per year, we're talking about 4,000 additional heat deaths that wouldn't have occurred if there wasn't anthropogenic emissions of greenhouse gases to the climate system. This also translates to actually, about over half of all heat-related deaths over Brazil in that period could be attributable to the human influence. So the next thing I want to talk about is that in the BRIEF project, in the Bristol team, we don't only just use CMIP data in our health research, we are contributing to CMIPs as well. So we're contributing to CMIP 7, the detection and attribution MIP 2. We're running this model called HETCM3B ESM, pretty long name, but it's a Bristol version of an older Met Office climate model. It's a coupled model. It's relatively old, but it performs very well. And the advantage of running that is that it can be run at high speed because it is a previous version of the model. So to put the speed into context, if we run a 172-year historical simulation, this model will take 2 to 3 days, whereas a complex modern model will take months. And the good thing about it is that we can then run very high large ensemble members to study the extremes, and we can also better sample the uncertainty space. So this is where I'll stop, and feel free to grab me for more discussion about the project. Thank you.
So now we're going to move on to how next generation Earth observations are helping to address the health impacts of climate change. So Rochelle Schneider from ESA is going to chair this section. And if Emma, Benjamin and Anna can come up and maybe sit at the front so you're all here for your presentation.
So good morning, everyone. I'm Rochelle Schneider. I'm from ESA. I'm the Copernicus and Destiny Ecosystem Operations Engineer. So what does it mean? Is pretty much helping using Earth observation data in multiple programs inside the agency, and then particularly in health-related applications, using AI tools for that to support us in this project. So today I'm gonna give you a brief overview about the ESA Climate Change Initiative, because this is very important for us in not only in climate, but also in health-related applications. So for those that never heard about it, the essential climate variables are variables that support us to understand the state of the climate. And then for that, the GCOS has elaborated the definition of these essential climate variables to support us on this. And we have come up with 55 definitions of these variables. And then from these, 36 can benefit from space-related observations. And then the Climate Change Initiative at ESA is supporting us to collect this information from multiple satellites and create a single data set. And we have at the moment 30 variables that can be on this portfolio of ESA Climate Change Initiative. What is the benefit of using Earth observation data for these specific variables is that we are able to provide global coverage of this information and then long time series. So we have satellites that are with us around 20, 30 years collecting this information for us. And then the resolution of this information is also valuable and can also come in the resolution. When we say the temporal resolution, like how often we can collect this information, and then the resolution of these images that we can obtain the information. And this data is also validated, provides uncertainty around this information. And this, of course, is available open free for everyone to use it under the website of climate.esa. So connecting this with projects related to Paris Agreement, I just bring 2 examples, but we have plenty of interesting use cases in our website. I invite you to have a look on it. So in terms of health, we recently have issued a tender that we invite people to use this climate change, the Climate Change Initiative Essential Climate Variables dataset for supporting people on the topic of health. And in this case, in multiple related subtopics. So for example, the exposure to heat, pollution, and also infectious diseases. And we also have done an activity on cities and understanding cities and urban environments and interaction with climate change. So some other activities, and then this is a little bit not necessarily the climate office at ESA, but in our lab, which is an AI hub inside the agency, is based in Italy, is focused in Earth observation and AI. And in this case, I bring you just briefly some examples of how we have done this connection with health applications. So here I will bring just how we connect observations, the digital twin data, and then simulations from a variety of data sets to support different topics of public health applications. So as you might know very well, we have issues in terms of be able to tell how people are exposed to the environment in different places. So sometimes we might have some ground stations, temperature, air pollution, ground monitors, but we don't have this everywhere, but we have people everywhere. So when we overlap this information, we see that there are mismatches between where people live and then where we have such information. And then when something like this happens, we really don't know like the exposure of everyone everywhere to be able to say the impact here is stronger than there. So the way that we found to cover this is using satellite data for that. And then, of course, a variety of different sources of information. So as you see in the top, we have a connection with Copernicus satellite data, but also NASA satellites, and then also the simulations of data, like the climate models, which are like by far really important for us to be able to do such work. And then where the AI enters in this place is to support us to reconstruct this information in where we have patches, then we reconstruct and we are able to develop this information of daily information in the last 10 years. And then we have this data set to be able to connect with health data. How do we connect with health data? I bring here just an example that you can check later how we have done it. So in this case, we use air pollution as a combination of to understand the impact of people being exposed to different PM 2.5 levels in different places across Great Britain. And we connect with different policies in this case, because we have the global policies on air pollution, we have European, in that time, European Commission related regulations that we should follow, and then also the national regulations for that. So how do we understand if we use these 3 different policies, what would be the impact on people on this? And then you see the difference in years of the exposure of people to such level of pollution. Another example that I'm also very happy, this is a very close collaboration with UNICEF. They came to us very interested in using AI and Earth observation for children. And we set up a team to collaborate together in how we can forecast dengue outbreaks, having them like every single week meeting us and then designing this project in the way that this would be valuable for them. And the most beautiful thing here is like we usually forecast dengue outbreaks as a generic total population mindset. But in this case, they were really interested in setting a specific age group for that, which are children. And in this case, from 0-19, we have to do a special forecast for this specific group, which was a great challenge for us. And we just absolutely love it to do it. So here you can see the outcomes of this project. Initially, we have been listed as one of the global top 100 AI solutions for SDGs from UNESCO. UNICEF select around 10 projects per year to give a spotlight showcase showing that these were the best projects of the year, and we will happily were being selected within this short list. Wellcome Trust also provided to UNICEF a support to continue evolving on this project and developing a digital platform for people to play with this data set using our algorithms behind this modeling system. And recently, we also have a publication that you can have a look here. And then all this information is open and free. So all the algorithms, all the data is available there. So very drastically changing the topic, but I would like to provide you a bit overview on what else we are at ESA be able to support health applications is the Destination Earth project, which is a project, a European Commission initiative that is a collaboration between ESA, ECMWF, and UMETSAT, 3 different organizations with different roles, but working together in delivering this initiative. So ECMWF is the organization responsible for delivering these digital twins in a higher resolution, including urban heat island inside of the modeling, which is something that Year 5 at the moment is not including on it. And the ESA is responsible for the platform, the portal for people to come and work with us. And then why this portal is so important, because it's where the users come. In this case, is a different type of users, can be experts and non-experts. So our role here is to be flexible and be able to create services and applications that will identify with users in different areas and in different types of needs in this case. So we have a rich catalog of what we call it services, applications, and demonstrators. And this is running under the European Sovereignty Cloud Solutions, and we have a lot of connections of Earth observation, climate and projections data transform into a different way for people to see it. And then here is just a quick example of all the services that we have at the moment operational, and they are using different types of Earth observation projections to support people in different needs. So I highlight here with the stars, for example, where you can find CMIP data available for you to use it in services that are just to go there and then get the data in an easier way, or services that are using this data to provide you different answers. Okay, so here is just quickly showing you that we have demonstrators. What's the meaning of that? We would like to foster the technology behind these activities using this data, but having fun. So here is a game, is based on a normal Godot engine that we teach people how to use this data and learn at the same time what are the actions that they have if they change the lamp to a LED lamp or to another lamp, and then this will, what is the impact of it in the future. So I invite you to just play with it in the QR code. And then another activity is the Earth Pose, which is also the mindset of it, is remind you when you were young, playing this with different topics, but now we bring you to play with topics that is related to Earth observation and climate. So here I just briefly show you some other examples as well of colleagues at ESA that have been working with the Road Climate Research Program. And they use this they use the Earth, the observation model interface to also explore different applications on this. And I invite you to also check the QR code, a lot of QR codes for you today, to have a look at this later. So now I would like to invite you to remember in the beginning when I mentioned that ESA has done some activities on the health-related projects, and then I bring today with me these the consortiums that are working with this. We have awarded 3 projects related to that, and I will start speaking about the first one, and then my colleagues will speak later on about the other ones. So this one is a climate health adaptation through a new generation Earth observation, so it's changed. So this consortium, it's based on 3 years activities engaging with us to use Earth observation data, more specifically data from the Climate Change Initiative, the essential climate variables that I mentioned before, connecting this with health information, and then be able to understand better the vulnerability of people and then the vulnerability of our health systems. And the objective of this is not only apply the data and then demonstrate the risk, but also educate people on how to use this information with a new type of sector, which is what we're discussing today, the epidemiology, environmental health applications. And this activity is definitely will quantify the climate attributes of health burdens, and then also support us in understanding, okay, how to design an adaptation roadmap using Earth observation as part of it, which for us at ESA is crucial. So we have a lot of use cases on this that will demonstrate applications in different areas and in different health-related topics, and in which you can see here some of examples of it. And then, of course, as I mentioned, everything will be available on a GitHub repository if this is related to coding workflows, but they also are very active on social media to demonstrate their impact. So now I pass the word for the next project. Is it? Should I speak about it? Okay. So this is a second project that is a climate change and health emergency care, which is climate care. It's a different consortium with different goals. And in this case, they have to use Earth observation data as well for emergency medical services. So the aim of this project is each one has a different topic of health-related applications and demonstrate the value for different locations and also different topics of health applications. And in this case, is to identify health risks hotspots and its emergency services around Italy.
So climate analysis in African cities, Kayak, is a project financed by ESA and led by Vito, with Ahmad and the University of Ottawa as partner. So Africa is facing a huge population growth, going from 1.5 billion inhabitants today to 4 billion for the late century. And this growth is usually happening in cities where the high-resolution climate information is lacking. So the Kayak project is aiming to tackle this issue by simulating 54 African cities at 300-meter resolution. We have one African city for each African country. We focus on extreme heat, flooding, exposure, and adaptation measures. To do so, we combine 3 different models. We have the geodynamics model, which provide future land use growth map and population map. We have the Sahel model, which provide flood map, and we have the EarthClim model, which provide hourly high resolution output at 300-meter resolution for each of the cities. Some example of the result for the urban growth model. You see some striking number there on the table on the left. For example, the Niamey population is projected to expand from 2 million people to 22 million people for the end of the century under the SSP2 4.5 scenarios. Just to compare, here in the Greater London, the population is 9 million people. And Rwanda, for example, is going from 10 million to nearly 100 million for the end of the century, which is huge growth. And the urban growth model can provide the map of this growth that you can see some example there on the right from Bamako and Kigali. We have also the urban climate model, which provide hourly output climate output at 300-meter resolution. We aggregate this hourly output to climate indicator. For each city, we have a lot of different indicators, more than 20, like the temperature, the number of day with night over 28 degrees that you can see on the upper left. For Cairo, for example, on the right there, you have the urban heat island effect. You will see really the cities popping out of the map. We have also WBGT indicators because our model provides humidity, wind speed, shade, and radiation. So we can combine them to provide WBGT map at 300-meter resolution. And we did this for the 54 African cities. And depending on how the cities score in each of those indicators, we divide them into 4 different urban heat regime that allow us to better focus the adaptation measure for each cities. You can see we also combined the future urban climate result with the future urban growth map result. You can see on the left, this is for the present day, and the middle, this is for SSP2 4.5 scenario in 2050, and on the right, this is for SSP3 7.0 in 2075. You see there on the top, this is the map for Kinshasa and Brazzaville. You see the huge urban expansion of Kinshasa going to the south. We see some of the same kind of picture previously with the FuturePop data, but there we combine it with the climate data, and you see that, for example, the number of nights above 25 degrees increase from nearly 100, between 100 and 150 for the present day to more than 300 for the future by the end of the century. And we also combine our urban climate model with health indicator by combining the urban climate with the population data that the geodynamics model provide. And here it is the map for Niamey, for example. You can see that the total deaths per year attribute only for the heat for Niamey is nearly 1,000 per year for now, and it is projected to increase to 160,000 by the end of the century. If you need any other information about the project, there is this QR code, and you can contact me now or by mail later if you want more information. Thank you.
Hi, hello. My name is Anna. I come from Lisbon, from Plaza Atlantic Collab, and I would like to acknowledge 3 consortiums funded by ESA on different programs. So we are representing climate adaptation, but also the Digital Twin Earth initiative that Rochelle just presented. And I'm going to take you to a very short journey throughout these 3 projects because together they bring you a program and approach to use citizen science towards added value, downscaling services, climate services for health impact assessment and adaptation planning. If this works. So we are under an extreme heat right now, so I don't think I need to emphasize a lot on why this is important, but there are some things that are important to draw attention to. For example, the compounding effect of air pollution. Ozone tends to be synchronous with heat waves, with possibly some one-day lag, and both together bring us excess mortality in a meaningful way, and they have an additional effect. And for example, if you look at yesterday, And if you look at temperatures and then ozone here in the UK, you can actually see that during this heat wave, we actually had simultaneously temperatures that are well above normality, but also concentrations of ozone, which are already on unhealthy space. And this needs to be compounded for in terms of health impact modeling. Another issue which is important is the lack of detail. So as you know, global models and even regional models tend to have kilometric resolutions. And when we are talking about cities, we actually need to go up to the neighborhood scale, especially if you are talking about public health services or architects and urban planners that have to take a decision at the metropolitan or urban scale. And this is what we want to bridge the gap with. So there are dozens of citizen observations that we can take advantage of. We are working in particular with one sensor provider based in France. It's European Devices, low-cost sensors. For those of you here that come from meteorology, of course, they are not as reliable as the standard high-profile stations, but because the numbers are on the hundreds and the thousand scales, depending on the city, you can actually model the error because it's stochastic. So you can clip out the extremes and take benefit from that in terms of inferring the special pattern. So we already have very good predictability in terms of the when, if we are going to have a heat wave or not, and the background, let's say, mesoscale intensity. But what about when we are within cities or very specific locations where we need metric resolution instead of kilometric? That's what we want to solve. So we use synoptic background weather as the context. This can be applied on reanalysis, forecasts, on climate projections, methodologically speaking. Then we use Earth observation data as our downscaling predictor. So these are the high resolution part that I'm going to show next. And then we use machine learning just because it's better at depicting the extremes. But we always benchmark against linear regressions to make sure that there is an added value from machine learning compared to more statistical traditional metrics. So this is an example from Lisbon, where we come from. These are the stations that we have from NetAtmos sensors in Lisbon. As you can see, there are dozens of those. Not all are useful. Some stations are complete garbage, let's say. In terms of observations, a ballpark figure is usually on the 50% approval rate. 50% is not. Still, when you are talking about hundreds of stations, you have thousands of observations, and this is much more than we have for WMO stations, for example. So we can actually then pick up the synoptic signal, and here you are seeing a model from the weather forecast in Portugal provided by IPMA, the weather services, and we can go to 200-meter scale, which is what you are seeing here. It's not only about the resolution. What worries us the most is the precision as well, because it's not only an interpolation, and that's always our benchmark. What's the added value of this methodology compared to a simple interpolation to reproject the data onto a 200-meter scale? Yeah. And this is an example from a heat wave, a past heat wave in 2020 in Lisbon. And what you can see here is that you have these gradients of temperature. For those of you who know Lisbon, this is influenced by continental air masses. And there, and there you have the influence of the Atlantic Ocean and the proximity to the estuary, but you don't see the city. Now, if you pick up Earth observation-derived products like imperviousness degree, tree cover density, and typology, I'm just showing you an example. There are other examples we can work with. Or land use land cover, the standard forcing land scheme feature for any numerical weather prediction or climate projection. We can put these things into a dynamical format, and we can reach this, which is the downscaling based on these local scale predictors, which actually allows us to see the temperatures with much more signal to noise ratio compared to the mesoscale. Now, what can we do with this? There are two things I would like to highlight, and these are being done together in these three projects from different perspectives. So, for example, we can use land use land cover change scenarios. These are actually implemented scenarios from CMIP data, CMIP 5 in this case, 8.5 IRCP. And in this case, we are forcing the downscaling model to predict what could be the change in terms of the urban heat island effect in case we would change the land use land cover as a function of local regulations. These are actually foreseen green parks that are to be built and foreseen dense neighborhoods that are also foreseen to be built. So you can have a sensitivity analysis on policy making, and you can actually do this on different, let's say, locations and interferences with land cover. And then there is another kind of application, which is much more connected to health. Here we are presenting the digital twin Earth component Earth for Health project that we are now replicating in Clean for Health at the local scale, where we take advantage of data from hospital admissions and mortality in Portugal and Denmark to actually do the causality between these two domains. So we can go up to each admin unit to show what is the compounding effect of both ozone concentrations, just like I showed in the beginning, and heat wave intensities as a function of the local climate, because a heat wave in London is not the same as a heat wave in Lisbon or in innerland Spain. So we need to take into consideration the local acclimatization with a function that is non-linear. So each additional degree has a larger impact. And with this, I conclude. Sorry.
Thank you very much for those they're really interesting insights into how we can use Earth observation data. So now, if I can thank you as our panel, we're going to move on to some reflections from data users. So if I can invite, we've got Gaurav Godwani, who's Executive Director and Co-founder at the Civic Data Lab, Yang Liu, who is the Climate and Health Research Lead at PATH, Geetra Sengupta, Earth Observation Research Engineer at GMV, and Helen McIntyre, who's the Principal Climate Change Scientist at UK Health Security Agency. Okay, so if we'll start with some reflections from Gaurav.
So thanks a lot for this wonderful presentation. We feel CMIP as well as FuturePop and other applications are very relevant for the kind of work we are doing in India. Just to take you to the scenarios we work with, we are all facing extreme heat here, but a lot of countries in Asia Pacific has been facing this kind of scenario for a while. What we see the local government struggle the most with is combining hazard, vulnerability, exposure data sets together with coping capacity. What is the coping capacity of the government agencies to actually respond to these disasters in near real time and also ensure their preparedness beforehand itself to understand what are the risk hotspots. Now, let me take you to one of the states we work very closely with, the state of Assam, which is located in the northeastern region in India. You would have drink Assam tea, right? The very strong Assam tea, which is quite famous for its flavor. But Assam also suffers a lot of flooding every year. At the same time, Eastern India is now heating up. So we have a twin crisis, extreme heat as well as flooding. Now, the local district disaster management authorities struggle to combine all of this data together. So what we're trying to do is create a climate health data collaborative, which takes in data sets like WorldPop, which was referred here, marry it with public procurement data, marry it with satellite imagery data, losses and damages data, to see all these data sets together at one place, do risk level analysis, and something which they are able to consume better. So all the formats which we discussed are great, but how do we make the capacity of district administration officers to consume it on a daily basis? All of this information that's where we're translating some of these insights in the language they are comfortable with, in the platforms they are comfortable to use. Thank you.
Thank you very much. So next up, we have Yang.
Hi, everyone. I'm Climate Health Research Lead at PATH. I am also Assistant Professor in Infectious Disease Modeling at the London School of Hygiene and Tropical Medicine, trained as an infectious disease modeler. At PATH, we work on climate health data services and health modeling as well. Again, very thankful for a morning of great information. I'm particularly interested in the city application, so I'm definitely gonna come get you after the talk. So I think, because I think it's such an important aspect. Cities provide unique challenges and opportunities where climate and health meet each other, and like a unique opportunity to intervene as well. So I'm just very, very excited to see that level of resolution is getting increasing attention internationally from different scientific community as well. And I think another slightly more worried about maybe thing that is coming from me is because all these are involving great complexity, and they all come from like with great uncertainty as well. And then when we move on to do the climate health modeling, that introduces additional layer of uncertainty. So when we communicate to our stakeholder what is the appropriate way and how do we communicate, where does this uncertainty come from, I think is something that our communities should meet together and like strategize collectively.
That's me. Thank you very much. Next up we have Future.
Hi everyone. Thank you very much to the team of CMIP for having me today. I think today I've also got a flag of CMIP Marine Laboratories, where I used to just work a year ago and now moved to GMB. We're still working together. I'll bring the aspect of water quality and human health into the game here. Listening to Shubha, Dr. Shubha from behind, worked with her for many years. I'm going to talk in the voice of a nurse and a microbiologist because I worked with them. They constantly talk about data interoperabilities to bring medical data of what they call as fast healthcare interoperability, FHIR system, into Earth observation, to bring that to medical data and sort of Earth observation data together into one single platform. Microbiologists and doctors already are aware of the environment. Earth observation provides as an addition, as an indicator. It's not just the main bullet in the gun. And to work with Wellcome Trust in one of our projects called Wadim, the multidisciplinarity of Earth observation data, environment health is a very multidisciplinary topic, and then mixing together rainfall, elevation, and population density has given me better indication of predicting cholera than anything else. So that interdisciplinary really helped in the long-term game. And the last project that worked recently has made me extremely depressed. It's the conflict and of conflict damage mapping of health facilities globally. I worked in January, February, March, and global news and working on this topic and made me very depressed. But again, working with the urban areas and how health facilities are being damaged. That's sort of, I'm talking about privacy, I'm talking about understanding the complexity, a complex of terminology that we use in health and conflict mapping globally. That's something that we have to be aware and very concerned about. Thank you very much.
Finally, Helen.
Yeah, first of all, thank you to the organisers for bringing everyone together today. It's been a really interesting day to see some of the pieces of work going on. So at UKHSA, we focus on protecting health, primarily with a focus in England. So health is devolved within the UK. So we have a role in understanding what some of the health effects of climate change are going to be on the population. And part of the way we do that is through partnerships such as the health protection research units, which were mentioned earlier. So we're working with the Met Office and colleagues at London School on that. So it's great to see that included here. We have a focus on trying to understand and quantify some of the impacts. And so for places like the UK, which is not spatially a huge country, that spatial scale is really, really important. So for our projections data, we tend to use things like the UK CP18, because that's at the kind of temporal and spatial scale that we need for health. So we really need kind of daily data for that. So it's great to see the CMIP work and how that kind of sets in context some of the data that we get from that. In terms of what's been talked about today, there's a couple of things I scribbled down as we were going through. The heat indices work will be really interesting. Humidity isn't really incorporated well at the moment. I think for the UK, we're not quite into those upper ends of where the heat index really kicks in, but it's really interesting to know if that is something that's coming down the road for us. And then the importance of population. Whenever we talk about health, it's really important to know where people are. This is really important for things like urban heat. Work we've done previously shown that anywhere between a third and a half of heat mortality during heat waves is because of the urban heat islands. So that's really important to be able to capture to make sure we're understanding some of these health effects. And then just echoing some of the comments that others have made around challenges of connecting across different scales. I think, and just connecting up different data sets again for health, it's when we're dealing with individuals, everyone has their own individual vulnerabilities and risks. You know, what kind of housing people live in, for example, what existing health conditions people might have. There's a real challenge there around connecting across scales, which hopefully we'll be able to.
Thank you very much to all of our data users. I'll just maybe ask you to stay there. We've just got maybe 5 or 10 minutes for some question and answer. If anyone in the room or online has any burning questions they would like to ask. Yes?
I like the term burning question. So there's been a lot of analysis and a lot of, description of the problem, but no one has really put forward what could be scalable, affordable, sustainable solutions, and essentially sustainable from a financial point of view. So,
anyone got any thoughts on that?
So one thing I didn't mention is through the Health Protection Research Unit that we're working on, we are looking to map what evidence there is for cooling interventions with a view to trying to build that information into health impact estimates. For the UK, we've had to kind of look beyond the UK for this because we're kind of at the point where some adaptations are there, but not very many. So the evidence base isn't great for the UK. So we're looking much more broadly to see what evidence is out there, map what's available by sector, by intervention. And then hopefully once we've got that, we'll have a much better picture of where the evidence lies and more importantly, where the gaps lie as well, where we really have to fill them in. So we're just starting to dig into that at the moment. And we really hope that project will help answer some of those questions.
Great.
Yeah, thanks for all your time. One thing that really strikes me is we've seen lots of different approaches to how we bring perhaps the health and the climate data together. And I just wondered, you know, I suppose I'm coming from a CMIP world where we like to compare different methods and work out what's the best. Do you think there's prospects for doing that in the health climate space?
My background is more in the infectious disease aspect. I think in that sense, model comparison is a lot less straightforward compared to climate models because what's going in, what is happening in the model, what's coming out, what is a forecasting target, how are the model rated and evaluated? Is it just regular models agnostics or is it aligning to a specific decision-making criteria? We were actually just talking about this yesterday, being jealous of the climate community having this framework of comparison, but in the health community lacking this framework. So that being said, I think it's not something that I know very well, but I think that's something that we should definitely aim for. So because we're in Wellcome, we're also maybe if there's opportunity that could facilitate that in the future.
Thank you very much. I have a question for Gaurav. So I was wondering if you could expand a little on, give us more examples on what approaches really kind of help increase the capability of local authorities in using that data, putting it to practice.
So one thing which we found in our work is making all of these data sets more interoperable, having a shared metadata standard to make all of these data useful for them and connecting with the metadata standards they are using, then breaking it down to a dashboarding or a platform which they are comfortable using it. So while some of the platforms which we see outside may be very good in terms of resolution, in terms of technology, but they need to be simple enough for a district administrator to actually use it and download reports as and when they need. And then lastly, making it in the language they are comfortable speaking it. So a lot of time, good analytics, good insights remain restricted because they are not translated to the language which district administrators as well as citizens are able to consume. So a lot of effort goes into translating these insights and making it more reachable to the communities we work with.
Thank you.
I have a question for, I suppose, all the panelists, the ones up here and the ones previously. I'm curious if you can say a little bit more about what you see as both favorable and unfavorable changes that you've seen in the last couple of years as widely used AI systems increasingly become a way that people interact with the data and models that you produce and use or help other stakeholders to use.
That is a great question.
Oh. I've seen that. I've worked with like in terms of with microbiologists and doctors back in India and elsewhere. And I mean, if you're asking about uptake of AI, in a sense, it's more about like what they want is achieved. Then yes, AI. If it's not achieved, then even AI cannot do it. And it really comes down to the point of different languages, not just verbal language, but data language, different formats and different way of how we produce data, and is that being used in their system. A lot of it is coming down to that interoperability. Like that's what I've seen in terms of uptake. And yes, definitely like AI in terms of producing results, helping a lot. At the end of the day, it's about bringing that together in one box. And that's where the struggle that I day-to-day find working with the World Bank and others. There was a request to produce the data in Uber H3 hexagons. And then where does AI play a role in transforming Earth observation data into that? So it's about that that's where the AI has kicked in terms of data formatting. But anything else, guys?
I can jump into that as well. So I think my main job is translating data into insights and analytics. So I think the application of AI has been quite helpful in terms of making a lot of more complex model, maybe more accessible to users, like through terminology that has recently emerging, like vibe coding. But I think the downside for that is if there is a steep learning curve, a lot of time when you're using that kind of model, it's very difficult to tell when it goes wrong. So I think I'm still like, because I have appointment at university as well. I run regular capacity building with stakeholders as well. We're all kind of like meeting up every now and then to just collectively think about like, how are we going to approach this? Are we teaching coding anymore at this point? So I think that's one side of it. And I think another side of it is we're seeing the widening of the gap between HICs and LMICs again, because HICs have a lot more access to this kind of tool. So the productivity is erupting on this side, whereas in LMICs, even like if the internet is unstable, we wouldn't even be talking about access to this level of tools. So I think that kind of like, I guess I'm the AI boomer and doomer myself all in one. So like these two sides are definitely both on my mind right now.
Maybe Helene, do you want to just say something about how AI is starting to sort of be integrated into climate modelling?
Yes, well, we're using AI to kind of replace some of the uncertain parts of the climate models. So you might use Earth observations from clouds to put better clouds representation in the climate models. But also we're working much more now to, this is really at cutting edge. People are working towards data-driven climate models so that we can turn, the idea is that, maybe we'll be sitting here in 2-3 years' time and we'll be able to turn around those scenarios super quick because we can train on what we have and produce new scenarios quickly. But that's all, visionary and not produced right now.
So I think we're at time now. So I think we've got some networking time after with some lunch. So feel free to ask any of our panelists or our speakers today there, or use the Slido to give your ideas about how we can sort of build that communication and collaboration we've been discussing this morning. Because it sounds like if we can build those kind of cross-disciplinary relationships and collaborations and projects, that's where we can understand each other's challenges and issues, and also see where there's opportunities to learn from different aspects of this sort of climate information chain and down to impacts and outcomes as well. So I think that is just all I have to say is thank you very much, everyone. Thank you to all our speakers, to our panelists. Please sign up to our mailing list if you want to hear about the latest CMIP data that's coming out, and just grab one of us if you have any questions. Sorry. And and thank you very much to our host, Wellcome. So Felipe, do you have some closing comments? And just to...
Well, it's been a fantastic session, and I would really like to thank all of you here and online for giving us the opportunity to host this session and for your engagement. It's been great to see you so engaged, and thank you for that.